Welcome to the course where we learn necessary lessons from probability to become AI researcher. This is used in large language models, reasoning, reinforcement learning, image generation, video generation. It's also used in finance, economy, and a bunch of other fields. In previous 3 lessons, we learned about random variables, and here we will continue to learn about conditional distributions, multivariate normal distribution, and change of variables formula. And I have some examples that make it easier to understand. This is directly used in, for example, flow matching for generating images and video, but in many other things as well. Let's say we have a loaf of bread. Now the bread is gonna have the length and width. This can help you imagine probability distribution of 2 variables, 2 random continuous variables. So what I mean is, let's say we have one variable that corresponds to to length. And so it goes from 0 to 1. Let's say the bread goes from 0 to 1. Let's say you have a plane with x and the y axis. And from 0 to 1 on x axis is the length of the bread, and from 0 to 1 on y axis is the width of the bread. So we have 2 variables, and the height of the bread, that represents probability at that point. So height of the bread at 0.5 is like a probability at 0.5. That's what it represents. Another example, let's say we have a human. What's the probability that the human is 175 centimeters tall and 75 kilograms of weight? And so if we plot all of the possible heights of the humans and weights of the humans, then the height of this volume above that plane of height versus weight, the height of the volume shows the probability of the human being at any of the specific points. So this volume looks like a mountain, where the peak of the mountain is whatever the highest possible combination is, maybe 180 centimeters, 80 kilograms. And let's say we want to just slice this mountain at, let's say, 75 kilograms. And now we want to get probability distribution of all of the people, of height of all of the people who have 75 kilograms. So if we have value for one of the variables, what's the probability distribution of the other variable at this value of this variable? We will first encounter the following problem. When we were looking at all of the human population with all of the possible heights and widths, the probability of all of them, all of the humans or all of the places, all of the combinations of heights and widths combined was 100% in total. But when we just take 75 kilograms and all of the heights at 75 kilogram people, the probability is no longer 100%. So now we need to make it 100%. We need to make it go like from have 100% in total to make it a valid probability distribution. So first of all, we know the function for this slice, and it's given by the f of our value, 75 kilograms or 80, how much did I say, and y, which is a variable, remains a variable. And the area under this function, we need to make it 1, because it's not 1 right now. It needs to be 1 to add up to 100% to be a valid distribution. Because right now, without making it equal to 1, it's called marginal probability distribution at this value x1 that we picked, like 80 kilograms. And I talked about that in the previous video. But to make it conditional, we need to make it add up to 100% below this function curve. And there is just a simple mathematical trick how to rescale or change this function to make the area under it add up to 1. So imagine that right now we have the function of, so f of our picked x, which can be some number like 0.2, and variable y. So let's say the current area below this function is 0.7. If you want to make the area below this function equal to 1, we just need to divide by the current area of 0.7. And now, this whole thing, if we look at this as a new function, it will have the area under it equal to 1. So probability distribution under it equal to 1 or 100%. If this feels a bit unintuitive, why are we dividing function with the area to get the whole area equal to 1? Just look at the scores at a test. So if somebody got 160 out of 200, they got 0.8 or 80%. By dividing our value with the maximum possible value, we are scaling the range between 0 down to between 0 and 1, or up. So if these were numbers smaller than 0 and we divide them, it will scale up. It will always be between 0 and 1. If you divide whatever numbers you have with the maximum possible number, it will scale it to between 0 and 1. How this connects to our example? So we have a function, and imagine that these values here are dots or points or instances of that function. So maybe this point, this point, this point. So if we scale each of the points with the total number of points, or we scale each of the points on our function with the total area, then we will make the new total 1. So you see here, the new total here is 1. So this is 80% of the total, 90% of the total, 30% of the total. It's a little bit unintuitive, but with time, it will settle in. So that's how we make the area equal to 1. Every point on the function, that means the entire function, divided by the total area, will give a new total area equal to 1. So area under this whole function will now be 1. Now that we understand joint, marginal, and conditional probability distribution that I explained in this video and other few videos, we will go on to learning the multivariate normal distribution. So this is a 3D version of the normal distribution. Normal distribution bell curve is usually expressed in 2D, but there is also a 3D version. And I talked about 2D version in first video, I believe, or second, but I think first, in this course, which you can find the URL below in the description. We know that normal distribution, the 2D one, has mean and variance. We talked about that in the first video. So if our bell curve has actually multiple dimensions, we can no longer describe mean with just one dimension, one number. We need a vector of numbers, where each of the numbers in the vector tells us the mean of that variable, of that dimension. Like the mean, where the mean is on x, where the mean is on y, on z. So for our height and weight example, let's say the average height is 175 centimeters, average weight is 75 kilograms, so the mean would be a vector with those two values. And these are the coordinates where we can find the peak of the 3D mounting here. So highest, most amount of people is at this peak. The probability of the human being this is highest, this height and width. And the second ingredient is the covariance matrix. So in the 1D bell curve, we had variance, which was just a single number. But now we need to not only describe the variance, the spread of each of the variables, but also how they relate to each other. Covariance matrix is a square matrix where number of rows and columns equals to the number of variables. In our height and width example, it would be 2 by 2 matrix. So these corners on the diagonal, the top left and bottom right, are variance for the individual axes here, individual variables, variance of the individual variables. So if this is x-axis, it will tell you how spread out it on x-axis, like this or like this. And if this is y, it will tell you the same thing, how spread out it is on y. We talked about this in the first video in this course. It's well shown on this example. So you see, if we look at this 3D shape from top, it can be circle, it can be like a ellipse that's curved. And you can see on this curved ellipse example that as x is higher, the y becomes higher. So here there is a correlation between x and y. But on this perfectly circular one, there is no correlation between x and y. They behave like independent variables. So if x goes higher, it doesn't also mean that y will become higher, which here it actually does mean. If you look at any of these points, there is no point that like x is x here if you get away from center, because those points are actually pushed up, because if x is higher, the y will be higher as well for that point. In our case of height and weight, this should be correlated. So this should look like this one, where if the person is taller, it's also more likely that they will have more weight because they're taller, they're bigger. So this would represent our covariance and our 3D normal distribution. If the covariance between height and weight was negative, that means that as height increases, the weight decreases, which is not going to happen in this example, height and weight, but it can happen in other types of variables. So then you would get a diagonal shape, but in the other direction, the other diagonal. So as you increase x, the y will go down. So higher x and y goes down, so you get the other diagonal. And if the covariance is 0, that means there is no linear relation. So it would either be perfectly circular or it would be elongated along some axis. So it's not going to be like this. It's going to be either elongated like this if the covariance is 0, or it will be circular. These diagonals only happen if there is a correlation between the axes. So if the point is higher on x-axis, it will also become higher on y-axis, so it will be pushed up like this diagonally. Funnily enough, I was gonna make video on this paper, and we already have marginal versus conditional probability distributions here, so it's already useful to me today, what we just learned in this course. Next, the last thing for this video, very important, the change of variables formula. So the goal of this is to answer a critical question. Let's say we have a random variable x, and we're gonna denote random variables with a capital letter, by the way. And let's say we know its probability distribution, let it be p of x. And I create a new random variable y by applying a function to x. So y is equal to some function of the random variable x. What is the probability distribution of y? That is this one, p of small y. That's just how we denote probability distribution of y. So the intuition and why it's tricky. Let's imagine we have random variable x and it has uniform distribution between 0 and 2. So what that means, imagine x-axis starting from 0 until 2. You just have like this rectangle, and this is the probability distribution, everything below this line. And since area of that must be 1 for it to be a valid probability distribution, then the height will be 0.5. Because this is 2, this is 0.5, so then the area will be 1. It's written here. So let's create a new random variable y using a function g of x, or y is equal to x squared. So y is equal to x squared. So what does this distribution of y look like now? Maybe at first thought it seems like maybe this rectangle is just scaled up or something. But the reality is so weird. So this blue is our x that I was explaining. But look at probability of y. Based on value of y, the probability density. Both of the areas under the curve are same, are equal to 1. here the function for probability, so probability of x is 0.5 at any x. But here the function is probability of y is 1 over 4 times square root of y. Let's get a bit of intuition. So if we have interval, if we look at interval 0 to 1 on x-axis, 0 squared is 0, 1 squared is 1, so that will be mapped to also 0 to 1 on y-axis. But the interval from 1 to 2 gets kind of stretched to 1 to 4 on y-axis because we are taking square of 2, and that's going to be 4 now. But the area under this curve must remain the same. So that means if we are stretching it like this, then we need to reduce the height because we have limited amount of area. So if we are stretching, we need to also reduce the height. And why is this huge spike here? Let's see what happens here. Just take a look on x. If we have from 0 to 0.1, when we square this will get mapped to 0 to 0.01. So I had this 0 to 0.1 on x. On y, when we're gonna squish that so much, but the area will remain the same, so area will go up. The probability, it's like squishing this, but then this must go up, this area. So due to our function, the small numbers here will get pulled closer to 0, so probability here will go up, so the area remains the same, and numbers that are larger than 1 will now get stretched away from the 0, so in order for area to remain equal, it needs to have less probability, less height here. But we don't need to draw these pictures every time we want to understand how the function probability distribution changes. We can just calculate the formula for this function directly from this or from the formula that we use to convert. So y is equal x squared. Although deriving this formula is maybe a bit difficult. But let's see the formula first. So we have the new function that we want to find. It's this function p of y that we just drew, the probability of y, random variable. That's going to be equal to the original function, which is just equal to 0.5 for x between 0 and 2. And 0 for other x's outside of this range, times absolute value of the derivative of x with respect to y. Now let's see this on an intuitive step-by-step example to understand this function better. So we want to find probability of y for any given y value. So where did y come from? If we have a value of y, we need to figure out which value of x it came from. So we know that y is equal to x squared. This is our transformation. So the x, to find the value from which this y came, we can say x is equal to square root of y. So this is called reverse lookup, and for any y, we know its original source was x, which is equal to square root of y. Now that we know from which x value y came, we can ask what was the probability distribution back at that original spot. We know that for every x the probability was 0.5 originally. And now we also need to figure out how much this probability was stretched or squashed at this point. Then we just use this mathematical trick that's kind of confusing right now. We'll see if we will dive deeper into this, but take the derivative of the reverse lookup rule. So just take the derivative of this square root of y with respect to y. And we're gonna treat this as the black box right now. So the derivative of this would be 1 over 2 square roots of y. So that will tell us how much the probability is stretched or squished at this place. And so we can just multiply original probability at that place with the stretch or squish factor. So this is the new density function. So 0.5 because the probability is 0.5 everywhere for the x times this that scales with y, that has this y value. So by plugging in this y value, you will get the probability at the y. By plugging in this value, you will get the probability. I told you to treat this calculation of stretching or squishing as a black box, as just a rule, and I think it's not important for now, so I'm not gonna be explaining this for now, but if you are interested, then you can ask Gemini or ChatGPT, or if this is valuable, I'm gonna also explain it at a later point. That's it for this video. This is part of the course, and check the full course in the first link in the description. See you in the next lesson.